Those of y'all at home, I want to let you know that there is some slides that were made available to the students in class. So I'll show it again. You can, hi. Okay, cool, I got it. Taylor, you're now famous on the video forever, so way to go. I mean, now you are. I didn't have to say your name, but I felt the need to. So, okay. Anyway, so if you want to pause the video, you could get a good look at this. Should I name her too, or should we make everybody famous? Hi, Annalise. Okay. Anyway, where did my stack go? Of course, this would be the moment that I totally.
Why are they brown?
Are they back there? They're all back there?
No, we have a printing again.
I'm so stupid. Okay. This is the best video of the day. Okay. Intermolecular forces. Before I go into exactly what we're looking at today, I want to remind you of something that we have already previously covered. So what I want to look at first is what is known as intramolecular forces. Intramolecular is not what we're covering today. It's something that we've already covered. Intra and inter, which is what we are doing today, those are important prefixes to know. Those are good like SAT prefixes. Like an intra is going to refer to something that stays within itself. Like an intrastate highway. All right, I know that y'all aren't all driving yet, but 1604 is an intrastate highway because if you can get on 1604 and you can drive on it forever and it never leaves Texas. All right, it stays within itself. The intramolecular forces are the bonds that I've already taught you. All right, it's the ionic, it's the covalent, it's the items that actually hold compounds together that we've already tested on. So if we were to look at a random compound, all right, if I were to say bond sulfur to iodine, all right, this is made up. But if I were to use this fake example as an example, the intramolecular would be that bond right there. All right, that would be a covalent bond because they're both nonmetals. Our focus today is something different. Our focus today are what are called intermolecular forces. There's 3 of them that I could list here, but we're about to go through them in depth, so I'm not going to finish that list. But here's the question that we ask ourselves today. If there were 2 of these Si molecules floating around, what would make them be attracted to each other? Not bond together. The bonding together is intramolecular. We're done with that. I want to know what would make these items be attracted to each other. And it's going to be these intermolecular forces that we are about to cover. So in a nutshell, everything that we're really asking ourselves today is what makes an item be attracted to a copy of itself. That's what everything is. What would make Si be attracted to Si or water be attracted to water? All right. We're not looking at what builds the Si. That's the past. We're looking at what attracts, not bonds, already established molecules towards each other. Sophia? It will be. It will be. Ultimately, charge is going to be a big deal. Now, again, there's 3 types of intermolecular. I'm just not listing them yet because they're about to get their own slides. If you look at the very first slide here, it lists them, but I'm not going to go over that. Oh, by the way, it's going to go across 1, 2, 3, 4. That's the way I'll be looking at them. So let's take a look at this second guy here that talks about phase changes. If you didn't have IMFs, if this list, sorry, IMF is short for Intermolecular Force. If you didn't have these forces that pull established molecules together, everything in the universe would be gaseous. Everything would be a gas, which would be really boring, right? It's hard to find other humans to hang out with if we're all just gases. But because once the SI was established, it wouldn't associate with other SIs. It would stay tiny and just go float away. But since there is attraction between established molecules, well, they can start to compile together. And if you get enough of them, it becomes a liquid. And if you get even more of them, it becomes a solid. Liquids and solids only exist because of the 3 types of intermolecular forces that I'm about to cover. So without today's lecture, gas, 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 gas everywhere. So looking at that second slide then, that makes phase changes when solids turn to liquids to gases or the other direction. That makes them solely dependent on intermolecular forces, the things that bring these guys together. Think about a block of ice. Do you have it in your brain? Got the block of ice? What's it made of? Water. It's made of H2O. It's all right. Ice isn't technically a wrong answer. It's made of H2O, right? But it's not just made up of one H2O. It would be gaseous if it were. It's made up of a bunch of H2Os, right? Even if it's a small block of ice, it's made up of a ton of H2Os that are congregated together. So if that's true, how do you make the ice melt? If the ice exists because there's a bunch of this going on that I haven't elaborated on yet, but if they're all being held together, how do you make it melt? Separate them. You got to pull them apart. You have to put in enough energy to overcome the attraction. You got to say, no, 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 pull them apart. And if you pull enough of them apart, the solid will become a liquid. And if you pull more of them apart, the liquid will become a gas. Phase changes are solely based on IMFs because there's no bond breaking in phase changes, right? We're not doing anything with the intramolecular. Those stay those. In the water, the H2Os are still bonded as H2Os. It's just the multiple water molecules are no longer getting associated with each other if you make the ice melt. So that's my big intro. What I really want you to be able to do is differentiate. Oh, I didn't refill my water. Is differentiate between the 3 types of IMFs. So let's do it. All right, so you'll see your very first one here is called London Dispersion Forces, is what we're about to look at. And here's the big umbrella for the first type of intermolecular force. This is the one that is going to describe non-polar molecules. Now, nonpolar is not a new word. If you need a reminder on what it means, remember a nonpolar molecule has evenly distributed electrons. All right, it's where electrons are evenly shared if it's non-polar. So let's look at a nonpolar molecule together. That's PP. You have to have a degree in chemistry to make such a joke. There are 2 good ways to look at this and know that it's nonpolar. All right, I've already trained you on this, but let's go through it. One way is the fact that it's an item that is bonded to itself. Now remember, that bond is intramolecular, so I'm not talking about IMF. But if the item is bonded to a copy of itself, then there's no pull of electrons because they're going to pull the exact same because they are the exact same. All right, so that's one way to tell that it's nonpolar. Another way is to look for symmetry. Do you see how it's a symmetrical Lewis structure? All right, if you split it down, it's a mirror image of itself. That's another, it doesn't always work, but for the most part, especially at this level, if it's symmetrical, it will be nonpolar. All right, for example, you see the blue structure there? Check out that blue structure. Do you see the symmetry in the blue structure? All right, yeah, that blue structure is a little more complex than PP over here. All right, but you can still analyze it if you give yourself enough time. All right, so symmetrical, that bottom one is nonpolar. Okay, so what would make phosphorus, y'all aren't handling PP anymore, well, so we're going to switch to phosphorus. What would make a phosphorus be attracted to another phosphorus? Now, this makes it look like phosphorus is diatomic, which it's not, but this is just for teaching purposes. But anyway, my question here is what would make these two guys be attracted to each other? Of the three IMFs that I'm going to go over, this is the most complex one to understand. So really bear with me as we get into this. All right, it's going to get easier after this example. Nonpolar molecules have trouble attracting one another because there's no charges anywhere. We need pluses and minuses. Opposites attract, right? You agree with that? Opposites attract. We need pluses and minuses in order to have them pull towards one another. Nonpolar molecules don't have that because by definition, the electrons are just totally shared evenly everywhere, and there's no charges. So what the heck is going to pull them towards each other if, well, there's nothing to do it? Have you ever watched a balloon pop in slow motion? I'm going to show you a video tomorrow of a balloon popping in slow motion because now I feel like you're missing out on your childhood. But YouTube it. If I have a balloon, look, I'm holding a water balloon. Do you see it? What color is it? Red. No, it's purple, stupid. Okay, if I take my purple water balloon, all right, and I throw it at the whiteboard. Can anybody tell me what the water balloon does when it strikes the whiteboard before it pops? It expands. Yeah, it strikes the whiteboard and its shape expands along the surface of the whiteboard, and then it pops and water goes everywhere. It changes shape more dramatically than you think it does before it pops. With that in mind, I'm going to draw my top phosphorus here, kind of more like an orbital way. I'm going to draw him as a circle. So this green circle is the phosphorus, all right? And what I'm going to do is I'm going to have that phosphorus fly through space, and I'm going to have it strike a surface. And when my phosphorus strikes that surface, here's what it's going to do. It's going to change shape for a moment, just like the water balloon. But when it strikes that surface, the electrons that were evenly distributed are going to be shifted to one side. Now, what charge do electrons have? Negative. So if, when it strikes that surface, if all of the electrons were to shift to that side for a moment, this side would have a partial negative charge since all of the negative particles are hanging out over there. Now, if you're like, what the heck did you just draw? That is an unfinished 8. It means partial for our purposes. This is a partial negative charge because upon changing shape, the electrons were distributed heavily to one side. If that's true, if that's partially negative over there, because all the electrons are over there, what do you think is true about the side that lost all the electrons? If you lost all those negatives, over here, there's a partial positive for a time. And if my other phosphorus does the same thing, not as pretty of a picture as I draw it faster, but if it does the same thing, guess what we suddenly have the ability to do? Not bond. That's definitely okay. I'm glad someone said that. Bond is not the right word. Like it's like wrong. All right, because bond is intra, not inter. So careful. That's one of the biggest pitfalls. But yeah, there can be an attraction here between the positive and negative, between the positive and negative, and suddenly the two phosphoruses here will pull together. This entire idea is called London dispersion. Of the three IMFs we're going to cover today, this is the weakest. This is the easiest one to pull back apart after it happens because these charges don't even really want to exist because it's a nonpolar molecule, right? So if something forms a liquid or a solid using London dispersion, it doesn't take a lot of energy to pull it back apart. Yes? So they'll hang out near each other, right? And hopefully, and the idea would be that if you were in an area where there are a million of these, and this has happened, they could all start pulling together. And when that happens, you'll have a chunk of phosphorus that you could actually hold, right? But then if you melt it, if you like put a heat source towards it, well, you won't have to put very much heat towards it because it's London dispersion and it's really weak, and that energy will start to pull them apart. But what this is doing is it's the process of taking this gaseous form, putting enough of them together through London dispersion to make it into a liquid and eventually into a solid. Yeah. Yes. Will you give me water? I'm about to die. Thank you. Am I about to be poisoned? I will regret. I'm just kidding. Miranda's good. All right. Let's talk about water balloons again for a moment before we move on. Again, the next two IMFs I cover much faster than this stupid London dispersion. All right. Look, see the water balloons? This water balloon here is small, and this water balloon here is big. All right, I've got the small water balloon and the big water balloon. If I throw both of them at the whiteboards, which one will change shape more? The big one. The big one has the ability to change shape way more than the small one does because there's more, for our case, there's more electrons, but there's also more surface area in the case of the balloon. Focus here, and then you're going to write it. Larger nonpolar molecules can have stronger London dispersion forces. Listen again. Larger nonpolar molecules can have stronger London dispersion forces. Larger nonpolar molecules can have stronger London dispersion forces. Oh, that was really fast. Oh, you were being nice. So I didn't mean to just run you on an errand. Thank you. Larger nonpolar molecules can have stronger London dispersion forces. And what I want to do is draw your attention to the slide, and you'll see the word polarizable. Find the bold word polarizable, and that's the word that describes the sentence I just gave you. It's actually a good vocab word because it makes sense. Like it started as nonpolar, and if it's really big, it's more polarizable. You can give it these charges more heavily if it starts larger. You can go when she gets back. Sorry if my brain doesn't remember things. Are there any questions over London dispersion? Remember, nothing today is a bond. It is all just an attraction. The other two do not rely on nonpolar, they rely on polar. So let's look at the first polar type of IMF. All right, we are now on the slide that says dipole, dipole on it. Now, before I get into polar, I want to revisit electronegativity. Oh, look, the golf chicken is famous now. Golf chicken forever. Okay. Electronegativity, this is review. We've done this already, but as a reminder, electronegativity is an atom's ability to attract electrons. If you have a high electronegativity, it means you love electrons. If you have a low electronegativity, keep those electrons away from you. This was one of your trends. Remember when if you go this direction and this direction on the table, this happens. Which direction does electronegativity increase? Up and right. If you go this direction and this direction on the periodic table, electronegativity goes up. Now, this ignores the noble gases because they don't do anything with their electrons. Therefore, what is the highest, what element has the highest electronegativity on the whole table? No noble gases, can't do noble gases. Fluorine, right? Fluorine is as far right and up as you can go while ignoring the noble gases. Okay, so we have that in our brain now. That was reviewed. Let's go back to IMFs. Let's draw a new compound together. I can tell right away that this is polar. There's two good ways to do it, so listen how I figure it out. First off, it's an item bonded to a different item. All right, so I did use the word bond there because that's what I'm looking at. It's an item that is bonded to something different. That makes it automatically a polar bond. And there's no symmetry, is another way to say it. All right, sometimes you have to look at the symmetry because you can have a polar bond but have it cancel out elsewhere to make the molecule nonpolar. But again, that's an older skill that we can practice together if necessary. But we've got a polar molecule here, but remember what the question is. What would make an HCl be attracted to another HCl? That's what IMFs ask. Well, let's look at HCl for a second, though. The fact that it's polar makes the IMF part, the attraction part, way easier because there is always a partial charge here. We don't have to hit walls and change shapes or undergo any of that. I want you to watch how I show this. This is called a dipole. And in the dipole, you point an arrow towards the more electronegative atom. Do you agree that chlorine is more electronegative than hydrogen? Yes, because it's further right and up on the table, right? So when you show this dipole moment here, you point an arrow towards whichever of the two is more electronegative. And then it gets a little tail. Hey, what does that little tail look like? A plus sign, because the hydrogen is partially positive and the chlorine is partially negative because the arrow shows that the chlorine is hogging the electrons and electrons are negative. All right, so then if we have another HCl, which is exactly what we're looking at, we want to know what would pull these dudes together. Well, we know that this other HCl is experiencing the exact same dipole as the first one, and guess what can happen? Opposites attract. Now, I know it looks like I keep drawing this X thing. That I'm just showing it from my picture. They don't line up like this. What would happen is the HCl here, well, it's floating through space. It would come and align itself easier over here so that the Cl could attract to the H. All right, and then there'd be another Cl over here, and then another one could come and attract to the H. And then it could just keep linking over and over and over again to build or to change the phase to eventually a solid. Yeah. You don't have to draw the dipole. It's just the question. It's based off of the dipole idea. We know that chlorine is hogging the electrons because of its higher electronegativity. This is just a chemical way of showing why that partial negative exists. The higher electronegativity is always the partial negative between the pair. This is dipole-dipole. Because dipole-dipole, right? I mean, really, it refers to the fact that the atom contains a plus and a minus, which is 2 poles. But yes. Yes, I'm sorry. Yes, that is exactly correct. The question was, does London dispersion only work with nonpolar? Yes, the moment you identify that you are dealing with a polar molecule, London dispersion is not your focus. Now, I didn't make this point in the other classes, but you're the first one to ask that question, so we'll tangent for a second. Polar molecule, don't write this, you don't need to know it for honors, but just for food for thought, polar molecules can do London dispersion, right? They can, but we don't care. It doesn't matter that they can, because polar molecules also do dipole-dipole and the other one, which are stronger. So even though a polar molecule can change shape and disperse electrons and do everything London dispersion does, the stronger forces are already pulling them together, so it doesn't matter that they can do that. But if you were taking a test and you were to say that this only undergoes dipole-dipole, well, you're wrong, because it does London dispersion too. It's just who cares? Well, I mean, anybody that said it was wrong. She doesn't know. Okay, let's go on to the last one. How am I doing on time? I feel like I'm not doing well. 53. No, I'm not doing well. Okay. Anyway, the very last one is hydrogen bonding. If you take a look, we're on the back now. Hydrogen bonding has the very worst possible name. It is a stupid name. They did not ask my permission to call it hydrogen bonding. Why is it a terrible name for an IMF? Because it's not bonding. All it does is confuse students. All right, so it's a bad deal. All right, someone made a mistake. But here's the good news about hydrogen bonding. It is dipole-dipole. It's the exact same thing. The only difference between hydrogen bonding and dipole-dipole, what makes it stronger, because this is the strongest IMF, is it has a very particular set of things that are attracted to each other. And here's what it is. To make it be hydrogen bonded, there has to be an H bonded to an O somewhere, an H bonded to an N somewhere, or an H bonded to an F somewhere.
What?
Hang on, I'm getting there.
You guys have all 3 of those?
No, just one. Yeah, it's this or, yeah, it's an or. No, you asked it because more than one person was thinking it. That's how that works. So I'm glad you asked it. All right. So with that in mind, let's take a look at the most famous hydrogen bonding compound, which we've already talked about today. What compound is that? Right? It's water. Well, it's 2 waters, right? We know that water is being held together by an intramolecular force that is covalent, the covalent bond. I want to know what intermolecular force would pull them together. Well, in water, where's the dipole moment? H to O. Really good. The dipole moment goes this direction, right? Because oxygen is more electronegative than hydrogen. And if we know that that's the way the dipole moment works, then we know that all of the hydrogens are going to be partially positive, while the oxygens are partially negative. And what happens next? There's the attractions, y'all. Opposites attract. This is hydrogen bonding. Well, there's probably other waters over here that they're connected to, right? Hydrogen bonding happens because one of those three requirements is there.
There's no rules.
No.
Okay.
All right, look at the second to the last slide that talks about melting and boiling points. I've already kind of made this point here. Refocus. Remember, phase changes exist because of all of these things that we've been talking about. So look here, I want you to absorb this. Don't write for a second. It would make sense that if one item, if you were comparing two things together, and one of them had a higher boiling point than the other, that the only difference between those two things would be their IMFs. Since intermolecular forces determine boiling point and melting point and those numbers that you associate with things like how much it takes to like boil water. Well, if you were comparing two different things together and I was like, which one of these things has a higher boiling point? Really what I'm asking you is which one of these two things has stronger IMFs? Because if the IMFs are more towards the hydrogen bonding side, which is the strongest, they're going to take more energy to pull apart. But if something is more towards the London dispersion side where it's really weak, lower boiling point. Doesn't take as much energy to disrupt London dispersion. So you can put what I've showed you on how to identify these things along with melting and boiling points. And that's what I want you to do. Look at the very last slide. There's a series of questions there. Question 1 and 3, I know 3 has multiple parts. Questions 1 and 3 are self-explanatory, but question 2 in the middle is based off these drawings up here. Look here. Question 2 looks at those drawings. I want you to take a minute and get as far as you can get on answering those questions to the best of your abilities. What's up?
London things, they also like attract slower because they take more energy.
No, not necessarily, because part of that is going to be based on the size of the atoms. The velocity at which things happen is mostly attributed to mass of the molecules. So
then how come if you were to what? But you just said that if you were to boil two different things, but one's a London thing and one's a hydrogen thing, and the hydrogen one would boil fast.
the attraction between them, I know, but that isn't necessarily based off speed. It'd be like having two really small magnets and two industrial magnets, right? It takes a lot. I mean, it's not about speed. It just takes a lot more energy to separate the two strong magnets. Hey, I am going to draw cards. That's why Aspen's out there. They're called isomers. I'll give you another minute to figure it out, and then we're going to talk to some people. No, you don't have to do it. These are your notes. Just do it. Do whatever. I'm not going to check. Just going to ruin your day by calling on you.
I never call my cards. I've done it before, and it still happens. That was what I wanted to do. That just means wanting to know. Nothing.
All of them are that. Remember, that's all IMFs ask. If it's going to give you a compound, and then you ask, how would it attract a copy of itself? All right, let's go over to cluster 3. It's totally you. Seat 5. Hey, 3, 5. I know, and this is like not the way to say thank you for getting me water. But it's the okay. So take a look. Which molecule is capable of forming stronger IMFs? Nitrogen or water? It would definitely be water. All right, because water forms what type? Hydrogen bonding, and nitrogen would be London dispersion because it's an N with an N, making it nonpolar, making it London dispersion. Let's go over to cluster 1. Seat 2. Hey, 1, 2. Is the black or the blue structure have a higher boiling point? She said the blue one. Do you agree or disagree? Now remember, we actually identified earlier that the blue one has symmetry and is nonpolar. If it's nonpolar, then the IMF is London dispersion. If the IMF is London dispersion, the boiling point is automatically lower. Whereas the top one is obviously polar. And what type of IMF can the top one do? Hydrogen bonding. See that HO right there? It can do hydrogen bonding because it matches one of the 3 requirements. All right, I'm about to run out of time, so let's go through these next 4 real quick. We'll do them individually. Let's go over to cluster 3 again, because, yeah. Seat 1, Aspen, it's you. Xenon. If a xenon is near another xenon, what type of attraction could pull them together? London dispersion. Nonpolar, they're identical to each other. All right. Oh, and Aspen is dead. Okay, that is bad. All right, let's go over to cluster 6. Oh, Aspen, it is going to be you, though. I got you. Hey, Aspen, what about H2S? Now, I'll let you know right now, without drawing the Vesper, it's polar. So which type of IMF does H2S do? Her guess is dipole-dipole. Do you agree or disagree? I agree. Just because it has hydrogen doesn't make it hydrogen bonding. It has to also have NOF. All right? So, dipole-dipole. Yes. Yes, you need to know the NOF. All right, but they're all right next to each other on the periodic table. All right, let's go over to cluster 2. C5. Hey, 2-5, what about CLF? I have a CLF and a CLF. What brings them together? But they have to be because it's Cl bonded to F and they're different items. So since they're different items, they have different electronegativities and there will be a dipole. Dipole-dipole. No hydrogen. The last one is a trick. It's ionic. You'll have a great day. Ionics do not do any of this stuff. Y'all did amazing. Oh, I won't see you tomorrow, SAT, boo. I'll see you Thursday.
And I'll see you never.